Welcome and thank you for joining. In this lesson, we are going over the graphs of polynomial functions. So we're going over the entire curve analysis. And so far, we have looked at examples of polynomial functions. And I decided to make things a little bit more exciting here. So we'll try to graph the function f of x, which is given as a product of a polynomial function first degree with a radical function, which is the third root of x squared minus 4. So I'll start off with the domain. In order to determine the domain of this kind of special function, we have to look at the domain of each factor. So the domain for the first factor, since it is polynomial, would be any real number x. So let's look into the second factor. We have the third root of x squared minus 4. I wanted to imagine if this expression inside the third root ends up being some positive number, we can third root a positive. If this expression ends up being 0 or has a value of 0, we can third root a 0. That would be equal to 0. And if this expression ends up being negative, then we'll say that the third root of a negative would exist. And for this, I would try to remind you of the third root of negative 8. So that is equal to negative 2. So what that means is that no matter what the value of x is, or no matter what the expression here becomes, the value of this function will be defined. So we will happily and proudly announce that the domain of this function is any real number x. I'll wait for the range until I finish graphing this function because I don't know exactly what it looks like. But I will start off with finding the x-intercepts by making y equal to 0. So 0 equals x times x squared minus 4 to the power of 1 over 3. I'm just converting the third root here into an exponent of 1/3. So for the product to be 0, then x must be equal to 0, or x squared minus 4 must be 0. So what that means is that x squared minus 4 will be 0 if x squared is 4, or x equals plus or minus 2. So therefore, we're going to say that the x-intercepts for the graph of this function will be at x equals 0, positive 2, or negative 2. Let's continue with the y-intercept. But we kind of know that since we found the x-intercept at 0, that means the y-intercept must be at 0 as well. So I will make x equal to 0. That's a traditional way of finding the y-intercept. So f of 0 would be equal to 0 times the third root of 0 squared minus 4. Multiply anything by 0, we get 0. So the y-intercept is also 0. And again, we know that since the x-intercept is equal to 0, x equals 0 is on the y-axis, so that's why we get the y-intercept of 0. So I'm emphasizing, or I'm mentioning these points because they help us think a little bit faster when we're graphing functions, and speed matters in thinking. It advances our thinking. So next we want to study the behavior of the function, so where it's increasing, where it's decreasing, and for this we'll ask the first derivative. So we're going to say that since f of x is x multiplied by x squared minus 4 to the power of 1 over 3, the derivative of it will be equal to, so you see we have a product here, which means that we have to use the product rule. So the derivative of x is 1 multiplied by x squared minus 4 to the power of 1 over 3. And then the derivative of x squared minus 4 to the power 1 over 3 will be 1/3 x squared minus 4 to the power of 1 over 3 minus 1 multiplied by the derivative of the inside. So we have a little chain here. So multiplied by derivative of x squared minus 4, or by 2x. And then we also have to multiply here by x. So let's make this look a little bit better. We have x squared minus 4 to the power of 1 over 3. And now we'll combine the monomials 1 over 3, 2x, and x. So that will make 2x squared over 3 times x squared minus 4 to the power of 1 over 3 minus 1 would be 1 over 3 minus 3 over 3, or negative 2 over 3. Because we want to study the sign of the derivative, then we will have to factor this. So what we normally do is we look for common factors. Remember, we have two groups of terms. So we have this first group and this one. So the groups of terms are separated by a plus or a minus. In this case, we have a plus. And the things we look at are the common binomial. So in this case, we have a common binomial of x squared minus 4. So we'll take that out. And the power that we're able to factor is the smallest power that exists in the expression. So we have 1/3 and negative 2/3, which means that negative 2/3 would be the common power. Another thing we like to take out is the denominators. So we have a denominator of 3 here, so we're going to take that out as well. And let's see what we are left with. So for this part of the expression, we have x squared minus 4 power 1 over 3, but we've taken negative 2 over 3 out. So what that means is that we have to subtract the power that we have taken out. So subtract negative 2 over 3. And since we're taking out 1/3, it means that the coefficient of 1 must be divided by 1/3. So 1 divided by 1 over 3 equals 3. So we're going to write 3 here. And now you see when you multiply 1 over 3 by 3, we go back to a coefficient of 1 here. So we have explained this before in class, but just a refresher again. Next, we are going to look into the second group of terms. So 1/3 is out, 2x squared is still in. X squared minus 4 power negative 2 over 3 is all out, so that's all we're left with. So I'm going to rewrite the derivative equals. Now you see that we have a negative exponent. We want to make that positive, so we have to bring it down to the denominator, where the denominator 3 is waiting for it. So we get x squared minus 4 to the power 2 over 3 here. Now in the numerator, a few things that we want to look at is we have 1 over 3 minus negative 2 over 3, so which is basically plus 2 over 3. So 1/3 and 2/3 will add up together to make 3/3 or 1. So basically this entire thing here is equal to 1. So what that tells us is that x squared minus 4 is to the power of 1 here, which means that we can start multiplying by 3. So inside the brackets we'll have the 3x squared minus 12 and then the 2x squared here. So simplify just a tiny little bit more. And we have 5x squared minus 12 divided by 3x squared minus 4 to the power of 2 over 3. So we need to find the critical points. So for critical points, we make the derivative equal to 0. Remember that the critical points are at wherever f prime of x is equal to 0 or f prime of x is undefined. And this is the reason why whenever we have a derivative in rational form, we have to study the signs of both numerator and denominator separately. So we're going to say that in the numerator, we have 5x squared minus 12 equals 0 when x equals plus or minus the square root of 12 over 5. So simplify this, plus or minus 2, and then the square root of 3 over 5. In the denominator, we're going to say that we have x squared minus 4. So I'm going to take up the whole denominator here, equal to 0, which will happen when x squared minus 4 is 0, which is true at x equals plus or minus 2. So we found 4 critical points here, and we're going to use all 4 critical points to study the sign of the derivative, first derivative. We're going to build our chart. We got to place the numbers on the number line. Now, you probably want to use a calculator to see the actual decimal value of plus minus 2 root 3 over 5. And that is because it is kind of hard to see where exactly that would be located. You can estimate it in your head. This is going to be less than 1, so the root is going to be also less than 1. So multiplying by 0 point something will give, basically a number that is bigger than 2 for the positive, less than negative 2 for the negatives. So therefore, we're going to say that the numbers must be placed accordingly, starting with negative 2, which is the smallest key value. The next will be negative 2 root of 3 over 5. The next key value would be 2 root 3 over 5, and the last one will be at 2. So we are going to list the numerator, the sign of the numerator, the sign of denominator, and lastly, the sign of the derivative. So f prime. And lastly, we will decide on the behavior of the function. Of f of x. So I will drop the perpendiculars from here. So in the numerator, we have the zeros, 5x squared minus 12, right here. In the denominator, we'll have the zeros at negative 2 and positive 2. The zeros of the numerator will make the derivative equal to 0, whereas the zeros of the denominator will make the derivative undefined. Now let's decide on the sign. So the numerator, as you can see in here, 5x squared minus 12, is a quadratic that opens up. And for a quadratic that opens up, passing through two x-intercepts, we're going to say that the shape is going to look something like this, which means that in between the zeros, the numerator will be negative. Outside it, positive. For the denominator, we have everything positive except for the sign changing inside x squared minus 4. So we'll say that x squared minus 4 being a quadratic that opens up, we'll have the zeros at negative 2, positive 2. So it will be negative between its zeros, positive outside it. So let's marry the signs together. Two positives will make a positive. A positive divided by a negative will make a negative. Two negatives will make a positive with a negative, and two positives, a positive. So we're going to say that when it comes to the behavior of the function, we'll have an increasing and then decreasing and then increasing and then decreasing again and increasing function. Now, notice that at the points where the function changes from increasing to decreasing, then the function will hit a maximum. At the points where the function changes from decreasing to increasing, then the function must hit a minimum. Now remember that the domain of this function is any real number x, so even though the derivative is undefined at the critical points, the function will still continue to show min and maximum points, right? So it's still a critical point for the graph of the function. So since we're at it, then we are going to state the min and maximum values of this function. So we're going to say that at x equals negative 2, the function will have a maximum value, which is equal to f of negative 2. And the value of the function at negative 2 would be equal to, so let's find out. So we have negative 2, and then negative 2 squared minus 4 third rooted. So third root of negative 2 squared minus 4, and that would be equal to 0. At x equals positive 2, the value will have a minimum, and the value of it would be f of 2, so 2 times the third root of 2 squared minus 4, which is again equal to 0. So I'm going to list the maximum point at negative 2, 0. So a minimum point at x equals 2, y equals 0 here. And what we are going to do next is find the y value of the function at negative 2 root 3 over 5, and x equals negative 2 root 3 over 5. So at negative 2 root 3 over 5, we have the value of the function at a minimum. So we'll say that the function will hit a minimum, which is equal to f of negative 2 root 3 over 5. And for this, we're simply going to use a calculator, so we'll find out the value of the function is 1.812. And at positive 2 root 3 over 5, the function will have a maximum. And the value of it will be equal to negative 1.812. So let's plot all the points on the graph, on the chart first. So we said that we have another minimum at negative 2 root 3 over 5 and 1.8. And negative 1.8 actually. Sorry, let me fix this. And at positive 2 root 3 over 5, the value of the function will be positive 1.8. Well, we can continue 1, 2, why not? And the function will mark, or will have a maximum here, so at this point. So next we will study the sign of the second derivative, with the first derivative being 5x squared minus 12. I'm going to rewrite it down here. Divided by 3x squared minus 4 to the power of 2 over 3. Then the second derivative, use the quotient law, will be f second x equals, so in this case we have 10x multiplies 3x squared minus 4 to the power of 2 over 3, multiplied together, right, the 10x and 3 in the next step, and then minus, the derivative of the denominator will be 3 times 2 over 3 x squared minus 4 to the power of 2 over 3 minus 3 over 3 negative 1/3 times 2x, so we have a small little chain in here, and then multiplied by 5x squared minus 12. And all this will be over 3x squared minus 4 to the power of 2 over 3 squared. Okay, so quite an interesting derivative here. We're going to go over the simplifying here a little bit patiently, because as you can see, it's kind of a heavier expression. So we have 30x x squared minus 4 to the power of 2 over 3. Down here we have the monomials. So we have the 3 and 3 here simplified. We have the number 2 and 2x that can multiply to negative 4x. We have x squared minus 4 to the power of negative 1 over 3, and then 5x squared minus 12. We do not want to expand right away, so we want to go over the factoring process first. And this will go 9x squared minus 4 to the power of 2 over 3 squared will make the power 4 over 3. So f second x equals, so let's take out the common factors. So we have a common factor of x squared minus 4, lowest power is negative 1 over 3. We have a common factor of x in here, so we're going to have 30 and 4 common of 2 as well. So we have 2x, which is common. And in brackets now we'll have 15. We have x squared minus 4 to the power of, so 2 over 3, subtract negative 1 over 3, will make a 1. And then we have minus simply 2 because 2x is out. So from 4x we have just 2. This is entirely out, so 5x squared minus 12. All of it will be over 9x squared minus 4 to the power of 4 over 3. Now let's continue the next step. We have f second x again equals. Now notice that this common factor here will be simplifying the denominator. So we have 2x in here still sitting there. We have 15x squared minus 60, and then minus 10x squared plus 24. And this power of negative 1 over 3 and 4 over 3 will simplify. So 4 over 3 minus negative 1 over 3 will make a power of 5 over 3. So 9x squared minus 4 to the power of, again, 4 over 3 minus negative 1 over 3, right? So that will make plus 1 over 3, which equals basically 5 over 3. So let's write that down. So we'll continue one more step here, simplify just a tiny bit more. So we have 2x, 15x squared minus 10x squared. That will make 5x squared. And negative 60 plus 24 would be equal to negative 36 over 9x squared minus 4 to the power of 5 over 3. Whew. We have a lot to talk about this second derivative because this turned out to be quite interesting. So we're going to find the key values of the second derivative. Since it is in fraction or rational form, that means that we have to find wherever the second derivative is 0 or wherever second derivative is undefined. So for this, we have to discuss the sign of both numerator and denominator. For numerator, we have 5x squared minus 36 equals 0. So x squared is 36 over 5, which will make x equal to plus or minus 6 over root 5. In the denominator, we have x squared minus 4, which can be equal to 0, and x equals plus or minus 2. So these are the key values we're playing with for the second derivative. So what we're going to do is build the chart now. All right, so I am going to have to make this small again. Okay, so we'll do this. Why not? Right here, so hopefully we have a little bit more room. I think we've missed a couple of numbers. Sorry about this. It's going to take no time. Okay. Okay, so let's draw the number line. On the number line, we have to place all the key values. We have quite a few of them. So the key values are negative 6 over root 5 in order. So we'll write them down. The next key value is at negative 2. And then we have 0. And then we have 2. And then we have 6 over root 5. Here goes negative infinity. Here is positive infinity. So we're going to study the sign of the numerator. The numerator is at 2x. Again, sorry, the numerator, we forgot to add this. Will be 0 at x equals 0. So the numerator will have 2x and 5x squared minus 36. So this is a cubic expression. The leading coefficient is positive, and the zeros are right here. Let me mark them, it's easier this way. So with the leading coefficient positive, then it means that the graph of the numerator will be going, up and then down and up again. So this will give the numerator a negative sign, and then a positive. See? I'm gonna drop the perpendiculars better. So, and then it will be above the x-axis, so positive, positive. It will come down below the x-axis, so numerator will be negative, negative, and then positive again. Now let's do the denominator. The denominator has the expression x squared minus 4, so 9x squared minus 4 to the power of 5 over 3. So let me extend these lines. The zeros of the denominator are at negative 2 and 2. So here we go, negative 2 and positive 2 means that since this is quadratic, it will open up here, which means between negative 2 and positive 2, it will have a negative sign, and outside it, positive. Now let's marry the signs together to study the sign of the second derivative. We'll say a minus and a plus divided by a plus, a minus, then plus, and minus, and plus, and minus, and plus. Now remember that the zeros of the second derivative will be at wherever the zeros of the numerator are. So right here, and right here. And at negative 2 and positive 2, the second derivative will be undefined and undefined. Now remember that the function is continuous for any real number x. So just because the derivative is undefined doesn't mean that the function is taking a break or anything. So now let's discuss the shape of the graph or the nature of the function. So the nature of the function here, second derivative is negative, concave down, concave up, concave down, concave up, concave down, concave up. So it seems that we have quite a few points of inflection, which is where the derivative is changing signs. So point of inflection, and then another point of inflection. Let me make this a little bit bigger. So the concave up intervals will be for the x values between, so these are all the concave ups, so 3 of them, negative 6 root 5 over root 5, comma, negative 2. And then the interval, so concave up again from 0 to 2. And concave up again will be from 6 root 5 over root 5 to infinity. The concave down intervals will be between, let's take a look, so negative infinity and negative 6 over root 5. It will continue again here with negative 2 to 0. And lastly, we'll have concave down from 2 to 6 over root 5. So when it comes to symmetry, we check for f of negative x. So negative x, the third root of negative x squared minus 4. So that's negative x, the third root of x squared minus 4. So this is different than f of x. So it's not even. So we're going to check negative f of negative x. So we're going to throw in a negative before the entire expression. So that would be positive x, third root of x squared minus 4. So that is exactly equal to f of x. So we're going to say the function is odd. So it does have odd symmetry. So since we are on the chart here, let's determine the increasing and decreasing intervals as per the chart. So we have increasing from negative infinity to negative 2. Negative infinity, negative 2. Increasing from negative 2 root 3 over 5 to positive 2 root 3 over 5. And then increasing from 2 to infinity. I don't think we have a lot of room here. That's called cheating for space. Okay, so we'll join the last interval, which is from 2 to infinity. So decreasing intervals will be from negative to negative 2 root 3 over 5. And the next decreasing interval is from 2 root 3 over 5 to positive 2. Okay, so we have almost a complete table here. I think we're ready to determine the graph, but we have to take a look one more time at the inflection points. So we have inflection points at 1, 2, 3, 4, 5 different points as indicated, but remember that because this is undefined, we don't know exactly what's going to happen in here. So we're going to wait and see until we draw the graph of the function. So we're going to say that the graph of this function will have the x-intercepts first at x equals 0, x equals negative 2, and x equals positive 2. So the y-intercept will also be right here at 0, 0. So the maximum and the minimum points on the graph of this function will be at the points as indicated here. So I'm gonna plot the maximum, which is going to be right at this point here. So negative 1 is slightly more than 1.5 and slightly less than 2 here. That would mark a maximum. And slightly there is symmetry here, obviously, so that makes it easier for us to draw the other side of the graph. So the other point will be somewhere in here. So that would be the minimum. So the next thing that we're looking into is the inflection point. Now, the graph of this function will start with a concave down. So, and the point of inflection would be at negative 6 root 5. And we find the coordinates of the y by simply using the calculator. So the point of inflection will be right here at x equals negative 3 is here. So that would be 1, 2, 3, where it's a point of inflection. So we'll have another point of inflection at 0, 0. And we'll also have another point of inflection right here in symmetry with this one. On symmetry. So close to positive 3 and a little bit more than 2. Somewhere here, that's a point of inflection. So the graph will start with a concave down. So it will be concave down. It will go concave up until it hits negative 2. Here the derivative, the first derivative is undefined, which makes the second derivative also undefined at that point. So the graph will have a concave down shape. And then continue concave down here, start concaving up, and then continue increasing. The derivative is undefined. The first derivative here is undefined, so when we grow up here, we have to move vertically. And at the point of inflection, right here, we have this function, and then it concaves up again. And this would be the graph of the function f of x equals x times the third root of x squared minus 4. So it will have the points of inflection, 1, 2, 3 of them. At x equals negative 2 and positive, the first derivative is undefined. As you can see, the tangent is vertical, slope of the vertical line is undefined. And if the first derivative is undefined at a point, then the second derivative will be undefined as well. So it cannot be an inflection point in here. So we're going to say that wherever the second derivative is undefined, the function will mark a very steep inflection point, let's put it this way, okay? So where the function will change the concavity, in this case from concave up to concave down. So pi. And the same thing will happen. So the point of inflection and the x-intercept is at the same point, basically. So this is a graph of this very interesting function. I hope this made sense, and I hope we found the instructions useful. We have one last thing that we want to add in here, that would be the domain. And as you can see, the range. And as you can see, the range is any real number. We have 5 inflection points. You can find the coordinates of the inflection point right here by substituting them into the equation of the function. And as x approaches infinity, you see that the values of y will approach infinity as well. And as x approaches negative infinity, the values of y will approach negative infinity. So I did prepare the coordinates at the inflection points ahead of time, so I will write them down in here. But again, we need to use a calculator for this particular question because it is, as a matter of fact, 6 over root 5, 3.95. And at x equals 2 and negative 2, as you can see, the function will have the value of 0. So negative 2 and, oops, sorry, not here. So inflection points right here. So we're also going to have negative 2, 0, and positive 2 and 0, where the function is increasing very, very fast. All right then. So as always, thank you for learning with me, and bye for now.